Okay, folks, this is a new lecture, lecture number 16, and the topic of the lecture is so-called two-way contingency table test, which is more often called test of independence, or sometimes chi-squared test of independence. The reason is, of course, we're going to have again the Pearson theorem that uses chi-square random variable as the test value. So what is this about? Well, we sometimes have the data that is categorical and not numerical, meaning that you can count certain things in a categories, but you don't have the values to attach to that. For example, I have the example here that story about sexual preference and HIV infection. You know, sexual preference of these are all males. Sexual preference of a male toward the male, which would be a gay, right? Toward female, that's called straight, and toward both, they will be called bisexual. And then you have the HIV positive test result and HIV negative test result. So neither of that can be quantified. You cannot say that you would have HIV positive with, I don't know, 3.7 or HIV negative, 2.2. You don't have any number attached to that. It's either HIV positive or HIV negative. So you can categorize a test result to be either HIV positive or HIV negative. You can count how many HIV positive you have, how many HIV negative you have, but you don't have any numerical value other than a count associated with that. So then you have a problem, of course, testing. You cannot do the testing in a typical way when we use numerical values. But you have a categories. So what we have here is we're trying to figure it out whether there is a relation between the sexual preference of a male and HIV infection. So we have a relatively small sample. It's actually a large sample because it's a sample of 30. We have 30 males here. And out of those 30 males here in my table, you can see we have 9 of them that are HIV positive. So, which means these are people that came to test, and we tested them, and we find out that 9 of the 30 is HIV positive, which means that they are infected. That will be 30%, right? 9 divided by 30, that will be 30%. So you got 9 divided by 30 is 30%. And then you have HIV negative, which is 21 of them. 70% of them, they came to be tested, are HIV negative, meaning the test shows up that they are not infected. Okay, out of this group, so that's a group of 30 males. Out of this group, we have 7 of them that are gays. We have 18 of them that are straight, and we have 5 of them that are bisexuals. So you can actually calculate all sorts of probabilities you might want to find out here. If you divide this number 4 with 30, you would get the probability that somebody's HIV infected and male at the same time. Gay at the same time. If you divide this number 2 with 30, then you would have the probability somebody's HIV negative, tested HIV negative at the same time being bisexual, and so on. So you can come up with some probabilities you might be interested in that. The marginal numbers here, so this is the main body of the table, these 6 values here. So again, these 4 are the 4 people, 4 males that are gays, they have sexual preference toward male, and they are HIV positive in this test. Okay, this number 16 means that you have 16 straight guys that are HIV negative. 16 of them that have a preference toward female, and they are also HIV negative. So the marginal numbers are telling you how many HIV positive you have, how many HIV negative you have. 9 positive, 21 negative. The marginal numbers here are telling you how many out of 30 you have gays, 7, how many straight, 18, and how many bisexual you have, 5. Okay, so those are the numbers here. Okay, so we want to find out whether the sexual preference has anything to do with the HIV infection, or whether the HIV infection has anything to do with the sexual preference. So, depending what you would call the first variable, or the explanatory variable, and depending what you're going to call the second variable, or the the response variable. So this is a response variable, this is explanatory variable. That's how I put it up. You can put it up something different. The reason is you have certain belief that the sexual preference has something to do with the HIV infection. The first one would be more of a explanation, and the second one would be more of a response to what the first one is. So that's why we call it. So this one on the top would be called explanatory variable, and this one on the side would be called response variable. So using conditional probabilities, which you probably study in 103, you could find some answers here. You could say, well, maybe there is a relation, right? Maybe there is a relation. And how do you find it out? Well, you check it out. What is the conditional probability that somebody is going to be infected if it's a gay? So the variable of infection, the variable sexual preference. So I'm looking for what is the probability that somebody is infected with HIV, and we know that that person is a male. So you know that it's a male. What is the chance now this is infected? So you look at those, how many males you have, not what is being a male, but being a gay, right? Sexual preference toward male, being gay. So what is the chance that somebody who is a gay is HIV infected? So then you look how many gays you have. You have 7. How many of them are infected? 4. So this is your conditional probability. 4 out of 7. You can check that out with your calculator to get a percentage if you care about that, and it comes up as 57%. So I got approximately 57% here. Okay, and then you look at what is the chance of somebody who is straight. There's a sexual preference toward female, so that's the condition variable. And what's the chance that that kind of person would be HIV infected? And then again, you look at it, how many straight guys you have. You have 18 straight guys, and 2 of them are HIV infected. So you have 2 out of 18. That's your conditional probability. If somebody is straight, what is the chance that that person is HIV positive in this group of 30? Okay, so you can calculate that again, and I'm coming up with the 11%, approximately 11%. Okay, so you have some answer here. You can see that the person who is a gay has a 5 times better chance to be infected than a person who is straight. So you can make some conclusions out of that. But those are non-scientific conclusions. I mean, they're educated conclusions. They're educated guess, but they're not scientific conclusions, because you don't really have, you can't tell me how sure you are that the being a gay is going to give you more chance to be HIV infected. You can't say that. You can say, oh, all right, you have a 5 times better chance, but that's pretty much it. But how sure you are in what you're telling me? So I don't have that. So I need to do the test here. And the test we're going to be doing will be a Pearson chi-square test, which is, I need to find out the expected values. I do have observed values, so these are observed values. I need to find out expected values, and I'm going to do the same thing I was doing that in the chi-square goodness of fit test, which is also based on Pearson theorem. I will subtract observed minus expected. I will square that. I will divide it with expected, and I'm going to sum that all, and that will be a chi-square random variable. So now I need to find out what is the expected value. Okay, what is the expected value? First of all, I have a setup of a test. The null hypothesis is there is no relation. No relation between the sexual preference and HIV infection. There is no relation between the HIV infection and sexual preference, or sexual preference and HIV infection. The H0, the H1, the alternative will be there is a relation. between sexual preference and HIV infection. Very simple stuff, right? The test value will be the chi-square value calculated again. I need to have the observed value, like 16, minus something here, that should be expected value, square that, divide that with the expected value, so again the number that I would have here, that's for this cell, and then you have to do it for this cell, for this cell, for this cell, for this cell, and for this cell. And you're going to have 6 of them. Add it up. This is going to be a chi-square random variable with 2 degrees of freedom. Now how do I know that? Well, I have 3 categories of sexual preference. That's the 2 degrees of freedom. I have 2 categories of HIV infection, positive or negative. That's 1 degree of freedom. So we multiply degrees of freedom of the first variable and the second variable, and we get 2 degrees of freedom. So you multiply 1 times 2. So 1 less how many categories you have here, 1 less how many categories you have here. So that would be 2, 1 less than 3, 1 less than 2, and you multiply that. So you have 2 times 1, which gives you 2 degrees of freedom. That is according to Pearson theorem. And again, we are not proving that theorem, we're not going into those details. Or the theory, that should be a graduate statistics theory, which we are not going to be doing. Alright? So that's going to be our test value. But I need to find out what are the expected values. I already said that in this group of 30 people, I have 9 out of 30 HIV infected. 9 out of 30 are HIV infected. I have 7 gays. 7 gays. So, if there is no relation between HIV infection, so we are assuming this is true, no relation, I should have 30% of the gays infected. So I would have 7 times, this is what we have, 9 out of 30, so this is 30%, 9 out of 30, and I multiply that with 7. So 30% out of 7 should be infected. Okay, so that's the number that goes here. Gays that are infected, are HIV positive. So I got that what? I got that by multiplying 7 times 9 divided with 30. Okay? Now you could use a calculator to calculate. Of course, I already have that calculator, so I'm not going to bother with that. I have 2.1. I'm saying this is 2.1. You can check that out. Okay? Now I have the 21 out of 30 that are not infected. That's 70%. 70%. 70% are not infected. 21 out of 30 are not infected. Okay? So if there is no relation between the sexual preference and infection, since I have 7 gays, I should have 70% of them HIV negative, not infected. So now you calculate that, and that turns out to be 4.9. Okay? You can use a calculator to find it out, it's not that hard. Okay, so that goes here. And I can continue further on for every cell like that. Okay? Again, 30%, 9 out of 30, 30%, 9 out of 30 is HIV positive in the group of these 30 people. How many straight guys I have? 18. So, 30% out of the 18 people should be HIV infected. If there is no relation between the HIV infection and sexual preference, 30% of the straight guys should be HIV infected, because 30% of overall sample is HIV infected. So I would multiply, this is 30%, I would multiply that with 2, or excuse me, with 18, because that's the number of, total number of straight guys. And now I get the expected value of straight guys that are HIV positive. And I come up with 5.4. Okay? Again, I have a 21 out of 30. the total number of people that are HIV negative out of 30 is 70%. 21 out of 30 is 70%. So you got 21 out of 30 is 70%. Okay, so this number is 70%. Okay, I have how many total of the straight guys I have? 18. 18 out of 30 that were tested are straight. So this, I should have 70% of them HIV negative. If there is no relation between the sexual preference and test result, positive or negative, I should have 70% of straight guys HIV negative. So now you calculate that and you come up with the so this one is 5.4 and here you come up with 12.6. So it goes here. Okay, and finally I have this group of bisexuals. I have 5 of them. So I have, again, 30% of them should be infected, 70% of them should not be infected. If there is no relation between sexual preference and infection. Because if there is no relation, in all of my sample I have 30% infected, so 30% of bisexuals should be infected. In all of my sample I have 70% not infected. That means 70% of bisexual would be not infected. So basically I'm just simply gonna use the number of bisexual here and come up with the expected value. We have 5 of them, right? Look at this number 5 here. And I got the, those numbers I got is 1.5 and 3.5 here. 1.5 and 3.5. So 1.5 and 3.5. Okay? But now if you pay attention how I calculate that, it's very easy. How do you calculate the expected value? There's a simple routine here. All you have to do is to fill the value here, all you have to do is to multiply the marginal value, which is 5, marginal value, which is 9, divided with 13. 30. 5 times 9 divided with 30. 5 times 9 divided with 30. That's how you get the expected value here. If you want to get the expected value here, you need to multiply the marginal value times the marginal value, 18 times 9 divided by 30. 18 times 9 divided by 30 will give you exactly 12.6, and that goes here. So again, this is the observed value, 16. The expected value is 12.6. How do I get 12.6? 18 times 21 divided by 30. Excuse me, it should be 21 here. So again, you multiply this one times this one and you divide with this one. This is actual value, and how does you get the expected value? So you multiply for the expected value, multiply this guy with this guy and divide by 30. Okay? It's very simple stuff. Okay? Now I was arguing that why is that before. I was saying, you know, you calculate if it's not, if there is no relation, then, you know, 30% should be infected, 70% should not be infected. So again, you want to calculate this is an actual value, you want to calculate, let's choose some other value, this one here. This is an actual value for, you want to calculate expected value, I get 2.1, how do you calculate that? You multiply this guy, you multiply with that guy, and then divide with this guy. 7 times 9 divided by 30. If you do that, you're going to get 2.1. Okay? You check it out. This is how those expected values are calculated. Now, marginal value in this table of expected values are the same. So again, you have 7 here, you add this is 7, you add this is 18, you add this is 5, you add this, you got 9, you add this, you got 21. So this is the main body of the table. And the marginal value is the same as the old table. And the total number of things, the total number of people, you have 30. Okay, and once again, you have to to make sure you understand this, that these are expected values. So they're not going to be, not going to be 2.1 guys. Nope. It's going to be either 2 or 3. But these are expected. This is expected value 2.1. So we're not looking for a particular number of people. We're looking at what is expected. So if there is no relation between the sexual preference and the HIV infection, we should have in this group of 30 2.1 of the gays infected. 2.1 of the gays will be infected. So this is a sexual preference toward males, so that would be gays, would be infected. Okay, very simple step. Now it's peanuts, the rest is easy. All you have to do now is to subtract, so you subtract the actual 4 minus 2.1, you square that, so this is a Pearson theorem, you divide it with 2.1, plus, that's this cell is 2 minus 5.4, you square that, you divide it with the 5.4 expected value. This is the same thing we did in the past. Again, 3 minus 1.5, so the observed value minus expected value squared divided with the expected value, plus next one, this one, main body of the table only, right? 3 minus 4.9, square that, divided with 4.9, 2 more, 16 minus 12.6, divided with 12.6. Yeah, now to write it, I forgot to square this. You should never forget to square this, because again, we have a complete mess if you don't do that. And I have the last one, two minus 3.5. You have to square that and divide with 3.5. That's a chi-square undervariable 2 degrees of freedom. Again, 2 degrees of freedom because you have 2 degrees of freedom here. For the sexual preference, there are 3 values, 2 degrees of freedom. We have 1 degree of freedom for infection, positive or negative. 2 values, 1 degree of freedom. So I have a 2 degrees of freedom multiplied with 1 degree of freedom, which is going to be total of 2 degrees of freedom. Not a total, but a product. Okay? So this is a chi-square undervariable by the Pearson theorem, chi-square undervariable instance, right? 1 value. And I don't know what that is, but we'll find it out. 7.66. Okay, the next step is the what's your conclusion here, right? Rejection criterion. Rejection criterion is just like in the goodness of fit test, a right tail only. This chi-square test in two-way contingency table, just like the goodness of fit chi-square test, is only right tail test. And that right tail must be the I'm gonna erase this one here. That right tail must be chi-square undervariable with 2 degrees of freedom. So RC, my continuation, I don't have enough space here, will be the chi-square undervariable, something like that. It doesn't have to be precise, but you need to know what you're doing. We're gonna use what? We're gonna use level of significance. I use in the paper level of significance of 5%. Whenever I have anything better, I just use 5%. And now you need to look at the chi-square table, and you need to find a value here where the 5% starts. I have the chi-square table with 2 degrees of freedom, and I found the 5% is associated with a number of 5.991. Again, this is a chi-square curve with 2 degrees of freedom. This is my test value. This is a critical value. My test value is here. conclusion, we have a rejection because the test value is passing the critical values. It is in the tail. That should not happen if we have the null hypothesis true. It should happen somewhere here, but it's not. It's somewhere there in the tail. Somewhere when there is less probable. It went there. So conclusion is we are going to reject this. We are concluding that there is a significant statistical significance in relation between the sexual preference and HIV infection. You can even go further. You can say what the reason is, because we have association clear there, that if you are a gay, you're more likely to have an HIV infection, according to what we find in the table. This is, by the way, no surprise. We know that already. In either case, it's been historical truth for this particular pandemic of HIV, right? Or should we say AIDS? Okay, so that's what we have here. All right. I also have to say something else about this test. This test is on too small of a sample, so scientifically this will not be recognizable as a test result. You'll probably get, if you do something like that and you want to publish your paper, you will probably be rejected because your sample is too small. It will not be acceptable, or you have too many categories. The reason is when we do stuff like that, there are basically two rules that you need to follow with a test like that. And one of the rules is that in general you should never have among the expected value, you should never have more than 20% less than 4. Now we have 3 of them: 2.1, 1.5, 3.5. That's 50%. We have 1, 2, 3, 4, 5, 6 of them. 3 of them are less than 4. So this is not acceptable. So if you write paper like that, somebody would say, this is not a good. This is not a good test because you have 50% of your expected value are below. Never have anything less than 1. Now we don't have that. We don't have any of them less than 1. This is 1.5, 3.5, 2.1. So we are not violating that. Again, you should not have anything less than 1, and you should not have more than 20% of the expected value less than 4. Okay, so we have a 6 expected value should not be more than 1 of them that is less than 4. So we are kind of violating here the rules of thumbs for two-way contingency table test. I need to say another thing also about this test. So how would you improve this one? Well, you just get a bigger sample. You need to find more males to test for HIV. That's it. Or you could reduce the categories. You can put the bisexuals and gays in the same categories. So you have one instead of 3 categories, you have 2 categories. In that case, this would add to this, and you would have 3 something. But if this would add to this, and then you would have 7 something. So that would improve the situation. You have too many categories, right? The sample is not big enough to have 3 categories of sexual preference. So that's the problem, right? There's 2 things about it. Number 1 is that this is single most often test in statistics. I think in social sciences this is the number 1 test you do all the time, in psychology and so on. So it's a very important test. Just because of that, it's a categorical test. It doesn't have numerical value. It's not a numerical test. I mean, it doesn't use numerical value. It uses counts. And that's what you have in sociology. You have social sciences. You have counts. You don't have that many numerical values. That's one thing about it. If you use a very small number of categories, if you use, I'm using here. The table is 2 by 3, right? 2 response variable categories, 3 explanatory variable categories. So I have 6 cells. If you don't have more than 4, then we usually use something else called Fisher exact test. That will be the next lecture, lecture number 17, which I'm not going to teach you. So you might want to read about that. So if you really need to reduce this to only 4 categories, you probably want to use that test rather than this one in particular. So the best way to do this test here if you're not happy with this, would be to increase the number from 30 to something bigger. Maybe 60 or 100. Okay? So, so let me use one test with a much bigger sample. Okay? We kind of have an idea that smoking, when the people smoke, it's related to their education. And their education is also related to their socioeconomic status. Socioeconomic status. So socioeconomic status is, we think, related to smoking. Okay? So we have federal workers. 356 of them. Okay? I divided them into 3 categories by the social economic status: high income, middle income, and low income. Okay? Then I divided them also into 3 categories based on smoking: the current smokers, improve a little bit, current smokers, former smokers, and people that never smoked. Okay? And then we count them. So we polled them. They told us what's their income and do they smoke. All right. So we get, out of the people that we consider to have a high income, we have 51 that are current smokers. Out of the high income people that were former smokers, we have 92. And they never smoked, there were 68. So the total number of people with high income is this group of 356 is 211. So this is my marginal total. Marginal value, because it's on the margins, that's why it's called. It's not marginal because it's irrelevant. It's relevant, but it's on the margin. Okay, out of people in the middle income level, we have current smoker to be 22. 21 are former smoker, and we have 9 people that never smoke. So the total number in the middle income level was 52 only. Okay, and then we have a low income level. Low income level we have 43 that were current smokers, or they are current smokers. 28 that were former smokers, and the never smokers, or the people that never smoke, is 22 of them. So then we have the low income level, we have 93 people. Okay, now you can also get the marginal by the rows. So the current smoker, the number of current smokers in this whole group is 116. The former smokers were 141, and the people that never smoked in the whole group is 99. And then of course you have the the total, and I already said, is 356, so you have to check it out. This adds up to 356, and this of course ought to add up to the same, right? Okay. So, again, just like before, you can use conditional probability to give you some information. What is the chance the person with a high income is going to be smoking? Okay, so now you have 211 of them. So this is the probability that somebody whom you know that has a high socioeconomic status is also a current smoker. I should say, if that person has a high income level, what's the chance that that person is a current smoker? So you look at 51 out to 211. 51 out to 211 would be, I don't know, you can use a calculator. And I'm getting 24%, approximately 24%. Okay, and then you look at the low income level. What's the chance that a low income level person is going to be a smoker? 43 out of 93. 43 are smokers out of the total number of low income level. Here is 93. So the person being current smoker while he has a low income level in this group would be 43 divided with 93, and I'm getting a 46%. Approximately 46, almost double, right? So you can make conclusion here. Non-scientific conclusion would be, if you have a, so I calculated this 46. If you didn't pay attention to what I was talking, I calculated by using fraction 43 divided with 93, and that's how I get 46%. Okay, so you can make conclusions. So you can say, people that have a lower income level are smoking more often than people that have a high income level. Okay, this time I really don't think this is actually causal. I don't think it's causal. I don't believe it's causal. I mean, if you have more money, probably you can spend more money on smoking, but it seems to be opposite. The people that have more money smoking less. Okay, so I think there's another factor here in the game, which is probably in education. The people that are better educated are less likely to smoke and more likely to have better jobs. That's what I think is in the game. So I don't think this is a causal relation. I don't think that one causes another one. But I still will call this one, socioeconomic status, is the explanatory variable. While the smoking is three categories. Smoking is response variable. So again, I'm considering it that way. You can do the reverse. In either case, now I need to calculate the expected values. So again, the expected value, you can reason that very simply is this way. I have 116 out of 356 that are current smokers. 116 out of 356. They are current smoker. That will be 33%, a third. So, of the high, if there is no relation between the smoking and socioeconomic status, I should have a third of the high income level smoking, third of middle income level smoking, and a third of low income level smoking. Right? That would be the expected value. They'll go here and here and here. I'm going to write the expected value straightforward in the same table. So I don't need to write two tables. I'm just going to have one table. So the expected value is going to be on the second place here. Right? You could say this is the observed value. The next one will be expected value, and the next one will be observed value minus expected value. So you have everything in one table, so you don't have to do writing of two tables. You could do just one table. Okay, so how do I get the expected value? So now you have to follow the story that we have previously. So I'm not going to be now doing explanation for every one of them. I'm just using routine. Marginal, expected value here. Marginal times marginal divided with this. So the number here would be 211 times 116 divided with 356. That's an expected value. Again, this is 1/3 of 211 should be current smokers. What that number would be, I come up with the 68.75. And you can see there is a difference, right? The expected value would be 68 17.75, but I have only 51. So there is a difference. So now when you subtract these two numbers, you're gonna get negative 17.75. Okay, that's the difference between the first and the second number. I'm just writing all three of them in the same cell, but you need to make sure you understand it. So the first one is what we have. The second one should be if there is no relation between the socioeconomic status and the smoking status, and the third one is just the difference of these two. Okay, here I have 22. The expected value will be 52 times 116 divided with 356. So it goes marginal time marginal divided with the total. Now I just need to calculate with the calculator. It's not that difficult. I got 16.94. When you subtract this, so this is again expected value. When you subtract this, you get the 5.06. Okay, I'm not going to write observe expected, observe minus expected. You just read from here. This is what those numbers mean. Okay. Now we have the third cell. Again, that will be 93 times 116 divided with 356. And the number you're going to get here is 30.30. You subtract these two numbers and you're going to get 12.70. Okay? And on you go. In every cell I'm going to just write one more down with a full calculation, and then I'm just going to copy the rest of it. Okay? What is going to be the expected value here? Alright? 52, the marginal, time the marginal. So again, this is the main body of the table. So marginal time marginal divided with the total. And if you calculate that correctly, you'll get 14.46. When you subtract that, it's negative 5.46. Okay? And on you go here, 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 and here. I need to find more values. Now here 83.57. And that will be again this time this divided with this, and the difference is 8.43. In here I need an expected value will be 20.60. Again, this number times this number divided with this number, and the difference is very small, so this is very close to what was expected. And the here I have 36.83. I'm reading my own lectures. You can find this lecture on Blackboard, right? So you're gonna check it out. It's written a little nicer, but without my talk explanations. And the last one I'm getting here is multiply this, time this, divide with this, and you get 25.86. And the difference is obviously going to be negative 3.86. Okay. So now, one forgot. This one. Okay. This one times this one divided with this one, and you got 58.68. Significant difference, right? From expected and actual. So these are the cells that you will look for where you actually have proof of relations, right? Where you don't have a proof of relation here, because apparently that's what is, the expected is similar to what it was observed. You don't have that much difference here. Also, expected is not that much different from what is observed, but some of them you have a significant difference. So this one, obviously, too big. Two numbers have plenty of difference, 16 something, 17 something between them, and some other numbers you can check it out, so you can see what the difference is. Okay, now the setup of the test. So what's our setup of the test? H0, no relation of socioeconomic status and smoking status. Let's put it this way, smoking status. Right? Current smoker, former smoker, never smoker. That's a smoking status. Okay? The H1 is direct negation of that, so there is a relation. Between socioeconomic status and smoking status. Okay? Sometimes it's also called there is dependence. There is independence between those, there is dependence between those. Which is very good alternative to say. Okay? And now you need to have a test value. The test value, I'm going to write everywhere. The test value, I'm not having enough space. So the test value is the Karp-Pearson chi-square random value. The same thing we did moments ago. It's going to be the difference square divided with the expected value. So it's going to be this guy, 17.75, square it. It's negative, but when you square it, it doesn't make any difference. Divided with the expected value, 68.75, plus another one. This one here, 5.06, square it, divided with the expected value, 1694, plus this one here, 12.70, 12.70, square it, divided with the expected value, 3030. The next one, so this is my test value, I'm really out of space, so I'm gonna have to squeeze it. Should be written down there, right? So I'm having the next one, 83.57, excuse me, 8.43, that's the difference. Square it, divided with expected value, 83.57, plus the next one, 0.4, square it, divided with the expected value, 2060. The next one, negative 8.83, square it, divided with expected value, 3683. The next one, 9.32, square it, divide it with the 58.68. Always the same story. The difference squared divided with the expected value. Difference between the actual and expected value. Observed and expected value. Square it, divide it with expected value. The next one, negative 5.46. Square that, divide that with the 14.46. And the next one, the last one, negative 3.86. Square it, divide it with the 25.86. All done. Well, the arithmetics of that follows. 18.51 is the number I'm getting. So that's my test value. So let's put it here. So my test value is 18.51. Okay. Chi-square random variable. The question is how many degrees of freedom we have. 3 categories of the explanatory variable. Socioeconomic status is explanatory variable. Has 3 categories. High, middle, low. 2 degrees of freedom. Smoking status is response variable. Current, former, never smoker. 3 categories, 2 degrees of freedom. So I have 2 degrees of freedom here, I have 2 degrees of freedom here. You multiply that, you get 4 degrees of freedom. my test value is a chi-square on the variable with a 4 degrees of freedom. That's the claim of Karp-Pearson theorem, assuming that H0 is true. Okay? So, the rejection criterion, that's the last thing you do. Rejection criterion will be based on the chi-square on the variable with 4 degrees of freedom. You need to find out what that is. In the table, of course, you don't need to find anything. You're just going to find everything that you need in the table. I am going to use 1% significance. I'm just doing that so to avoid this 5% all the time. So 1% significance, so I'm now looking here at this to be 0.01. Never mind my graphing, it's not a problem, it's just a sketch anyway. And I need this value here. Okay? So, chi-square tables, 1%, 4 degrees of freedom, 4 degrees of freedom, and 1% to be significance. I come up with a number 13.277. 13.277. Okay? Again, I'm using a chi-square random variable with 4 degrees of freedom because of 2 degrees of freedom, 2 degrees of freedom, 2 times 2, 4 degrees of freedom. And I'm looking for a level of significance of 1%. What does that mean? My conclusion is going to be at least 99% certain. So it's not going to be certain, of course, that's 100%. But my conclusion is going to be verifiable, justifiable with 99% chance, okay, or more. So whatever if I reject this null hypothesis, I'll be at least 99% sure that that's the correct decision. And I'm going to do exactly that, because this 18.51 is in the tail. The test value is in the tail. It passes 13.277. The test value is in the tail. I'm 99% sure that socioeconomic status has something to do with the smoking status, or smoking status has something to do with the socioeconomic status. They are not independent. There is dependence between those two. That's why this test is often called test of independence. The result of my test is that they are dependent. They are related. They are not independent. If you have a higher income level, it had something to do with your smoking. Or if you smoke, they had something to do with your income level. And we can go further. We can look at where the differences are, and you're going to find it here. Less likely, 51. Expected 68. It's less likely you're going to smoke. Current smoker. It's less likely you're going to smoke if you have a higher income level. Look at here. More likely you're going to smoke. You have 43 observed, expected 30. More likely you're going to smoke if you have a lower income level. Okay? So you look in those numbers, the numbers tell you the story. You can be a little more specific about it. If you have a higher income level, you're less likely to smoke. If you have a lower income level, you're more likely to smoke. That's what we see here. How sure I am in that? 99% or more. Because I was just testing this independence with 1% significance level. So when I have a 1% significance level, that means I'm certain in rejecting if I'm rejecting null hypothesis, I'm certain at least 99%. Another thing you need to check it out is about the expected values here. So I said already that we have two requirements here that we need to follow. We need not to allow that in our expected value we have anything less than 1. I don't have anything less than 1. It's obviously a much bigger number than that, right? Second thing, it should not be more than 20% of the stuff. I have 9 of them. I shouldn't have 2 or more less than 4. I don't actually have any one of them less than 4. So this is a good test. I have a large sample. That's a good test. And the conclusion stands on its own. That's a good conclusion and works. Okay? Again, this is probably the most often test you're going to be doing if you are going to be studying any social sciences. It's called, what I call it, two-way contingency tables test. It's also called Pearson chi-square test, whatever that means. Because there are a couple of chi-square tests, and all based on Pearson theorem, so you might want to call either one of them. But this one is often called Pearson chi-square test. It's also called test of independence, or chi-square test of independence. So whenever you run into something like that, chi-square Pearson test, or a chi-square test of independence, or two-way contingency tables chi-square test, or just two-way contingency table test, but it's going to be chi-square variable in the game. This is it. Okay? And another thing about it, this is always a right-tail test, like the goodness of fit test. The tests are based on the Carl-Pearson theorem or right-tail test. Why? Because if you go for the left tail, it'll be something small, close to zero. That means that those differences are very small, that these numbers would be very small, and that will be indicative of that you have a perfect independence. But we are not testing for that. We are testing to reject independence. We are testing to reject no relation independence. We are testing to find out where there is a dependence. So left tail test is not what we perform here. You could test how perfect is this independence, how perfect is this no relation, but we don't usually do that. Okay? It's possible. So it's usually right tail test. Or should I say 99% of the time. Unless somebody is really interested in how perfect is that no relation or independence. That would be the left tail test. Right? I'm done with this stuff. Again, this is a very important topic. It's a homework related to it. There is a homework related to it. It's a topic, again, if you're going to be studying social sciences, there is no way you cannot learn this, because you will at some point have to use it. It's also used in biology very often. So you study some science where you have categorical data as opposed to numerical data, so there's accounts, right? How many people are smoking? I mean, you're a current smoker. You can say, well, I'm a current smoker, I'm smoking 25 cigarettes a day, so I can probably, get some numerical value there. I'm a current smoker, I'm smoking 15 cigarettes a day. So there might be some, numerical data here, but we didn't use it. We just say, are you smoking or not? And we say, oh yeah, I'm smoking. Okay, I'll just list you here as a current smoker. So I'm not using numerical data. So whenever you're using categorical data, the data that fits categories, you get counts, but you don't really have numbers other than counts, then this test for independence. If you want to find two things that are related or two things that are independent, related as independent or unrelated as an independent, this is the test you do. Again, I have to point this out. This is, for social sciences, single most important statistical test. And it's also important for some other sciences like biology. Right? I'm going to be stopping this stream. I want you to do the homework on this, and I want you to read the lecture to see all of my numbers are from that lecture. And they're a little more nicer written there. Calculations are there. I want you to read that. Okay? I'll see you the next time.